Greetings, Chem 110H, Dr. Bevilacqua here. I want to go over pH, pKa's, and the use of mathematical operators. So P is a mathematical operator. What's a mathematical operator? Well, it's some mathematical process that we do to a function. So for example, we could take the partial derivative with respect to x and see the hole there? That's where the function's going to go. Or I think of this process as picking it up and sticking it next to a function f. And there's a hole here. I could take the second partial derivative with respect to x, and you'll see these two processes in a week or so when we start to move into quantum mechanics and we look at the Schrodinger wave equation. Another mathematical operator is log, to take the log of something. P itself means to take minus the log of something. So for example, we can have pH. Here we take minus the log of the H plus concentration. Actually, more formally, we would have the activity of the H plus ion. You'll learn more about that next semester and as you go along further in chemistry, but for dilute solutions, concentration and activity are equal to one another. You can also take minus the log of other things. So for example, in our research, we'll take P magnesium minus the log of the mag concentration, and we can also take P of a constant, pKa, minus the log of the acid dissociation constant. And I'll say more about this constant on the next slide. So you might say, all right, I understand how to do the math, but why bother? And there's two answers that I have to that question. The first is that concentrations of H plus and magnesium are often small, way less than a molar. As you know, a typical H plus concentration at neutral pH is 10 to the minus 7th molar. And that's kind of a mouthful, so it's more convenient just to say that the pH is 7. So it's really to take these awkward numbers and to make them more convenient. So we just need to be mindful that as the pH increases 1 unit, because this is a log base 10 operation, the concentration of H plus changes tenfold. And moreover, as the pH goes up, the concentration of H plus goes down, and that's because there's a minus in the P operator. And of course, you could think about it the other way if you wish. As the proton concentration decreases 10 times, the pH goes up by a unit. So just a little bit of mathematical operations to relate pH and pOH. Yes, in the same way that we can have P of different quantities, we certainly can have P of the hydroxide. Recall that Kw is equal to the product of the H plus and the OH minus, and that its value is 10 to the minus 14th at room temperature. And I can operate on both sides. Of course, whatever I do to one side of an equation, I must do to the other. I'm going to take minus the log because I've got an ion getting to pKw. I take minus the log of Kw and minus the log of the product of H plus and OH minus, and using the rules of logarithms, I can separate this out into two different terms, and then I recognize this as pKw, I recognize this term as pH, and I recognize this term as pOH, and I end up with this fairly simple relationship. pKw is minus the log of 10 to the minus 14th is 14, and so I have pH plus pOH is 14, or I can solve for pOH, that pOH is simply equal to 14 minus the pH. So in other words, if you give me pH, I can give you back pOH by using this relationship. And so let's look at what is a Ka here for a second in this box, because we're going to come back, we're going to refer to that in the table below. So first off, Ka is an acid dissociation constant. And so, for example, if I take some acid HA and I dissolve it into water so it's aqueous and it dissociates either a little bit or a lot, it makes H plus and A minus. And then I can write down the Ka, and that's defined as, well, we use the law of mass action. We just write the products multiplied together over the reactants. But what makes this a dissociation constant is I write the molecular form, and you should know that term. On the left is the molecular form. It's non-electrolyte. This species does not conduct electricity. And then on the right, I write the dissociated species. And that's the conventional way to write down an acid dissociation constant. Once I have this, I can define a pKa as minus the log of the Ka. And one thing, a rule of thumb to take with you, is that the lower the pKa, the stronger the acid. And I like to think of this by the same sort of rule of thumb that I gave you up here, that and let's just do it backwards, and let's in our mind substitute H with K. So as the pKa drops, the acidity increases. Okay, so lower pKa is for a stronger acid, and higher pKa will be for a weaker acid. So with that in mind, we can go ahead and then look at strong acids and weak acids. And I'm going to provide a table here, but I want you to remember that that pH is equal to, this is pH here, minus the log of H plus. It's not minus the log of Hx. So in other words, pH refers to how much free proton I have. If it's bound up in a molecular form, then that H is not acidic at all. Okay. Let's go ahead and put the table down. And we have three different rows here. One is a strong acid. So for example, that could be hydrochloric acid, your hydrohalic acids. It could be an oxyacid. Certain oxyacids, the rules we'll give in class, such as perchloric acid. We have weak acids like acetic acid, hydrofluoric acid, and then we have non-acids like, let's say, sodium chloride. And you should be familiar with the entries in this table. So a strong acid, again, a strong acid has a low pKa. The pKa is going to be less than 1. We saw in some cases, like in the case of perchloric acid in lecture, that pKa is actually minus 7. And if it's that low, it's leveled in water down to the pKa of water, which is minus 1.7. I'm going to say more about that on the next slide. A weak acid is in this range of 2 to 5. It's less than 7, but it's not super low. And then a non-acid like sodium chloride, the pKa is close to neutrality, close to 7, let's say in the range of 6 to 8. And so if I make up a 1 molar solution of a strong acid, which is 100% dissociated, we can go ahead and look over here on the right, then I know that the concentration of H plus is going to be 1 molar, and minus the log of 1 will be 0. So a 1 molar solution of HCl actually is pH 0, not pH 1. And then I can calculate the pOH from this relationship up here, that the pOH is 14 minus the pH. So I just go 14 minus this column to give me this column. 14 minus 0 is 14. 14 minus 1 is 13, and so on. And as I said, for a strong acid, it's 100% dissociated. It's a strong electrolyte. You'll remember back to the demonstration that we did in lecture with the light bulbs, and HCl 1 molar or 0.1 molar HCl, either one, strongly lights up all the light bulbs. A weak acid, like acetic acid, is only about 1% dissociated. But even so, it's still a weak electrolyte and can light up some of the light bulbs. And so if I have a 1 molar solution, then this will be 0.01 molar or 10 millimolar. H plus. If I had a 100 millimolar solution like in the electrolyte demo, then this would be 1 millimolar. And then in a non-electrolyte, all the H's, the protons are still molecular. There's essentially none free, and so this is a non-acid and a non-electrolyte. So I'd like to finish with a discussion of why the pKa of water is actually 15.7 and not 14, and why the pKa of the hydronium ion, which we saw in lecture, which leveled the perchloric acid, is minus 1.7. And so let's start out in the left-hand column here with the pKa of water. I'll write down the equilibrium for water, which you're familiar with. I'll write down the equilibrium constant using the law of mass action right here, and that's equal to 10 to the minus 14th. But then I'm going to go ahead and divide both sides by H2O. And when I divide this side by H2O, I get the full equilibrium from the law of mass action. And when on this side, when I divide by H2, I'm going to replace that with 55 molar, the concentration of water, which we showed in lecture. And you can show that 55 molar is equal to 10 to the 1.7. And so if I have 10 to the minus 14th over 10 to the 1.7, that's equal to 10 to the minus 15.7. And then if I take minus the log of both sides, I get that the pKa is 15.7, or that the pKa of water is really 15.7, not 14, when I take the 55 molar water into account. And that's important in physical organic chemistry when you're doing relationships, structure-function relationships between different acids. So now let's look at the pKa of the hydronium ion. Again, we saw that that's equal to minus 1.7. It's not 0. And so again, first thing we do is write down the equilibrium. This is H3O plus, and it's dissociating to give water and H plus. Or if we look at the reverse reaction, the water is a Bronsted base and a proton acceptor. We write down the equilibrium, and we realize that these two terms can cancel. And so this equilibrium is just equal to the concentration of water, which is 55 molar. I take minus the log of both sides in order to get the pKa, and I have minus the log of 55 molar, or minus the log of 10 to the 1.7. I end up with minus 1.7, and you can see where that comes from. Thanks for listening.